Hello, good morning, good evening, good afternoon, everybody, wherever it might be. Today we have a guest from Białystok, and his name is MCKEE, and he will tell us about Groupoids, Banach algebras. The floor is yours, the Zoom is yours. Take it.
Thank you, and thanks for the invite to speak. So this is joint work with Dr. Krasniewski and Krzysztof Bardani. So, of course, there's a groupoid C-star algebra construction that's been around for a long time. And more recently, things like LP operator algebras associated to groupoids have started to appear. Our goal in this project was to construct a general Banach algebra associated to a groupoid that's like universal in some sense, as the examples I mentioned as special cases. Let me start with this. Can you get rid of this?
Yeah, you can. I mean, just have something. I didn't create it, so I really don't know how.
Never mind.
Okay.
For me, the base space of a groupoid is a locally compact first-row space. Then the groupoid, the topological groupoid is X. So that's a set of elements which I think of as from an element of the groupoid starts at one point of X and goes to another point of X. And then we have these two maps. The domain tells us where an arrow starts. The range tells us where it ends.
Sorry, if you write that these arrows are from X to X.
Yes, I agree. And this is not so clear. It's not a function.
Yeah, it's not a function. So application of an arrow is a single point in X.
X is a bunch of
nothing more
points, and that an arrow is. Perhaps this is also clear. Then we have this composition operation, and we can multiply two arrows, which means drawing one arrow and then another arrow. But this only makes sense when the second arrow starts where the first arrow ends. And that's this here. Every arrow has an inverse, and this does what you would expect. The inverse arrow begins where the original arrow ends. First. I think of my unit space as sitting inside the groupoid as units. So if I think about either being an element of the unit space, that means eta is the domain of gamma, where gamma starts, and then the product of gamma multiplied by the domain of gamma is just gamma, and the same on the other side. Finally, it's a topological groupoid. So we have a topology on G, this set of arrows, and it makes the operations continuous. So for me, I'll be talking about étale groupoids. That means that these two maps, the range map of local homomorphisms. So for each point, there's an open set on which these maps are homeomorphisms. But This topology is importantly not going to be Hausdorff in general. There are some natural examples like that arise in nature, if you will, of groupoids, Ital groupoids, where the topology is not Hausdorff. And in the literature, often the Hausdorff assumption is there, and we wanted to get around this and capture these non-Hausdorff groupoids. So even though the unit space is Hausdorff, the whole thing in general is not.
Sorry, don't you assume that X is closed subset of G?
Yes, I guess that's built into my assumptions somewhere.
Okay.
So if you're like me and you come from group actions, then this is the prototypical example of an action of the group G on the topological space X by homeomorphisms. Then, as I said, my groupoid is just the Cartesian product of the base space G. Units are included as pairs where the group element is the identity element. And the domain of a pair X is just X. And the range is the homeomorphism coming from S applied to element X. So we think of the group element S as mapping X to the image of X from the homeomorphism, which S. And if you think of these things as arrows, then the formula for product and inverse are quite natural. So this is quite a good toy example, at least for me, but it's not really general enough to work with. So we can get a general enough example by relaxing assumptions and replacing our action of a group by homeomorphisms by an action of an inverse semigroup by partial homeomorphisms. So I'll explain what each of these data wants. S is an inverse semigroup. That means it's a semigroup set with an associative operation. And the inverse comes in because every element S has this unique generalized inverse S star. So the generalized inverse condition is these two things. S star S is S, and the other one S star S star. So two comments here. Of course, a group G is an inverse semigroup, and the generalized inverse is the actual inverse. And secondly, these two equations, you think of operator theory, it should make you think of partial isometries. Partial isometry and Hilbert space, something satisfying these two things. And when we come to represent inverse semigroups somewhere, we'll want to represent the elements of S as some kind of partial isometry. But that will come later. So that's S. Now what is this thing? Partial homeomorphism on X is a homeomorphism between two open subsets of X. H is a partial homeomorphism there's a domain of H, which is an open subset of X, a range of H, which is an open subset of X, and H is a homeomorphism from here to here. And in fact, the collection of partial homeomorphisms on X forms an inverse semigroup. The inverse of a homeomorphism, the generalized inverse, is the actual inverse, at least where it's defined. And for composition, you have to be careful, but you compose homeomorphisms on the largest open set where it makes sense to compose them, basically. So you need to take the intersection.
Sorry, in this inverse semigroup action definition, do you assume that that it is a semigroup homomorphism or inverse semigroup homomorphism?
I guess if it's a semigroup homomorphism, it's automatically preserves the inverse like
even if you don't have cancellation or something like that?
Yes, okay. Yes. Let's start. So, and with the other equation, this tells you that H of S star is the generalized inverse of H of S.
Okay, so saying that every S has unique generalized inverse, you mean that you have this star map from S to S. Okay, okay. Oh, I see.
As I said, then this action is a homomorphism from S into the collection of partial homeomorphisms X. Each applied to the element T, it has a domain and a range. These are open sets, and it's a homeomorphism between these open sets. And with all this set up, we can kind of copy the Groupoid structure from here, except that you need to quotient by equivalence relation. Work properly.
Sorry, I have still a problem with this definition of the homomorphism of inverse semigroups, because if you have this map from S to S, you must add something. For instance, that it is an anti-homomorphism. Because if you don't have cancellation, you can write something, and how do you know that this element, which
okay, well, I mean, maybe I was just lazy and should have written the inverse in here. Be happy. But like, yeah, it's a star.
So it's automatic.
It's a star preserving an arc between the inverse semigroups, between this inverse semigroup and this inverse semigroup. That's what I wanted.
And it is automatic that this star is an anti-homomorphism.
Ah, sorry, you're asking about this star?
Yeah. I would be sure if it was written that you have an anti-homomorphism from S to S.
Yeah, this star is a map from S to S. That's what I need here. For every S we can produce it.
And we assume that it's an anti-homomorphism.
It should be an anti-homomorphism, yes.
Because without cancellation, I'm not sure if
yeah, I see. Yeah,
could prove it.
Yes. So just a remark here. Later in the talk, we'll encounter inverse semigroup acting on other things. Here, the inverse semigroup acts by partial homeomorphisms in a set X. It could also act by partial automorphisms on a C-star algebra, for example. That would be C-star algebra isomorphism between two ideals of the C-star algebra. And we'll come across some of those later. The last thing about groupoids I want to mention is bisections. So a bisection of G is an open subset of G where the restriction to the range and domain maps are injected. In general, R and D are local homeomorphisms, and we want them to be actual homeomorphisms onto the image.
And so shouldn't it be called a local bisection?
Perhaps, yes. Some people emphasize, some people have a global bisection.
Mm-hmm. Usually.
Yeah. For me, bisection means local. So returning to our group action example, G acts on X, homeomorphisms. We have bisections given by these sets, the product of X with a singleton T.
And this is a global bisection.
Okay, yeah. So we should think of this as like T multiplied like times the domain of the homeomorphism HT. And from that point of view, it's obvious what a bisection for the inverse semigroup action is. We need to take XT star here, the domain of HT. These will be local bisections. So tying all these things up together, the collection of bisections forms an inverse semigroup. The product of two bisections is just the product of their elements. I mean here where the range of theta is the domain of gamma. So this product is defined. And here, if we fix eta, then the range of eta is an element of X. So there can be at most one gamma in the bisection U for which this product is defined. And that lets you prove that this thing is a bisection. The inverse, the generalized inverse of U is just defined by pointwise inverses. And
so if you call it local bisections, then it would be a generalization of a very well-known theorem that bisections of a groupoid form a group.
Yeah, that's true. So for me, global bisections of a groupoid form a group is the way I would say.
Inverse.
Okay. So from this, we get an action of the bisections of G as partial homeomorphisms on the base space of the groupoid X. So the action applied to a bisection, it has domain, the domain of the bisection, range, the range of the bisection. And it goes like this. It does the inverse of the domain map, which is homeomorphism, and then the range map, which is also a homeomorphism.
Sorry, can I ask what is P in front of homomorphism of X?
This P? Alpha. Yes, this stands for partial. This is to remind us that we have partial homeomorphisms.
Okay.
In contrast to
okay, thanks.
Previous slide where we had global homeomorphisms.
Okay, yes, there's the okay, perfect. Thanks.
So this example, if we take these bisections from the group acting on X by homeomorphisms, then this action is the same as our original action. So we recovered the original action from this action by bisections. That's easy to see if you just write down the definitions. So just to summarize, if we start with an inverse semigroup action, then we get a groupoid. And conversely, if we start with a groupoid, we get an inverse semigroup action, the one that I defined here. And everything works nicely in the sense that these two things are inverses to each other. So if we start with a groupoid, pass to this, and then pass back to a groupoid, we recover the original thing.
But any of these going in between, is your set X somehow fixed?
Yeah, so I'm thinking of a groupoid with this, like X is fixed as the base of my groupoid. Yeah. So this says that these two pictures are equivalent to each other. But for this talk, I am thinking that we're beginning with a groupoid, and the inverse semigroup is something like some data contained in the groupoid. Inside the groupoid, you have these bisections, and then you get these. They are equivalent pictures.
So they are equivalent under the assumption that it's an étale groupoid.
That's where étale.
Otherwise, this cross product would be much bigger.
Yeah, I couldn't make sense of this. So now we want to define an algebra based on the groupoid. And the definition requires us to be aware of these bisections that are. So just some history I mentioned before. There's a well-developed theory of groupoid C-star algebras. A lot of it from Renault's work. And people have asked and answered lots of questions about groupoid C-star algebras. And more recently, there's LP operator algebras coming from representing groupoids on LP spaces. Or Banach algebras associated to group actions. So usually if you have a group acting on, say, C0 of X, you complete it as a C-star algebra. But you can think of a Banach algebra completion of this thing. And we wanted to generalize this existing theory. So our goal is a general construction of a Banach algebra associated to the groupoid, and we should have some way to recover these existing things. So this says what our construction in the paper covers. In general, we work with twisted étale groupoids. They don't have to be Hausdorff, as I said. Our algebras are over the real or complex numbers. We can have some flexibility with the field. And yeah, I forgot to say they're normed by a family of representations in general. So for this talk, I'll forget about the twist completely. I'll spare you those details. I'll mainly talk about the complex case. There are some subtleties in the real case that I'll remark on if I have time. I'll also stick mostly to the Hausdorff setting. And the definition of the norm in the paper, we have to choose a family of bisections of the groupoid in general. And I will avoid making this choice or having to make this choice by choosing all bisections. as my choice. Okay, so my setting is an tile groupoid with a unit space X, Hausdorff topological space. So if you're familiar with group C-star algebra construction, you know that you take CC of the group, define representations of that, and that gives you a norm, and then you take the completion. For non-Hausdorff groupoids, the traditional CC of the groupoid is not so easy to work with in general. I mean, even like in the non-Hausdorff case, compactness doesn't work how you would expect very well. So this was the idea of COM. Instead of working with the traditional CC or G, we replace it by this thing, the linear span of genuinely compactly supported functions that live on bisections only. In the Hausdorff case, this one will reduce to the traditional continuous compactly supported functions. But in the non-Hausdorff case, they might not be the same. And this one we can work with. So I should apologize because I just told you I was going to stick to the Hausdorff case and then immediately started talking about the non-Hausdorff case. This view picture of CC or G informs our definition of the norm, which is why I'm
So by span, you mean the span in the vector space
linear
of
combinations.
all complex valued functions on G. Or what?
So we take linear combinations of functions f, which are compactly supported and live on a single bisection.
But you have to relate somehow this open subset U.
Relate to what?
For instance, if one open is contained in another, you are extending by 0, I suppose.
Yes. Okay. Yes.
Okay. So this is the same as the span on this is the span in the space of all functions, C-valued functions on G.
Yes, this span you're asking about.
Mm-hmm.
Yes. So we can define convolution on this in the usual way, and the involution as well. Makes sense here. So if you read a paper or see a talk on Groupoid C-star algebras, they probably define this norm. So in the group case, this has an L1 norm, and this is what we use to define our representations. But here there's no canonical thing to do, so we could choose this norm, which comes from the domain map, like this. Or we could use the range map to define. And this was Hans' definition, was to just take the maximum of the two. So we have this I norm is the maximum of these two things. Maybe I should have labeled them by D. This should be the D norm. This should be the R norm. But they arise in the L1 and L infinity context, not paper. So
could you explain why for D you have L1 and for R you have L infinity?
Yes, I was saying maybe I should have labeled this with a D and this one with an R. That's how they're usually labeled. But in our paper, we find them whenever we're working on LP spaces, and we represent them on L1 spaces. We somehow find this norm, which is why it has an L1 there.
I understand this L1 on the left-hand side. By why you have L infinity here?
This norm arises when we think of representations on L infinity spaces in our paper somewhere. So I have an L infinity here.
It's strange because in a groupoid, D and R are symmetric with respect to the inverse.
Yes, and there's some kind of duality thing going on here between L1 and L3.
So you mean that in this inverse semigroup setting, you don't have this symmetry. You have duality instead.
Is that the correct way?
But I think you told me about
Enable this just to avoid this problem. So just as I said here, normally to define a representation of CC or G, you think of homomorphisms which are constructive for this path. But we will put a different norm on this, and so our representations will be contracted with a different norm. So now I'm going to construct the algebra. So remember that F is in this new CC space. So it's a finite sum of these FUs, where FU lives on a bisection. So what we noticed is that the norms from the previous slide, if you just consider the I norm of one FU, you get the supremum norm. And it turns out that this is what you need when you work with representations. So I'll let you stare at it for a second and see that it's the supremum norm. If F lives on a bisection, then there's only one gamma here, so this sum disappears, and we just have the max of X in X, which is the same as the max of gamma in the bisection of this. So we get supremum norm.
Provided X is compact.
But F is compactly supported.
Yes.
Anyway, so.
Okay,
Yes.
Yes.
So these norms agree, and Bartosz's kind of foundational idea for the project, that this is what you need when we talk about representations.
So this could be interpreted in the way that extension by zero is an isometry in the infinite norm.
Yeah, that's a nice way of thinking about it, I guess. Yeah. So here's the lemma. There's a maximal norm on CC or G, which has this property that it, when you restrict to function living in one bisection, it's the supremum norm. And this maximal thing turns out to be submultiplicative and respects the involution. Here's the formula. So we look at all of the ways we can write F as a linear combination of functions living on bisections, and consider this quantity. So our norm is bigger than this I norm from the previous slide. So then we define the kind of universal Banach algebra to be the completion of CC of G in this maximal norm. that I just defined here. And this is a Banach star algebra because of the length. So this is like the universal one. I also want norm based on only some representations, basically.
Sorry, so the star is as usual.
On CC here.
Yeah, but what about compatibility between this star and this norm?
It follows because of the inverse accepted.
Yeah. So what's the relation between this star and this norm?
Yeah, it's involutive. It respects the
Involutive. What do you mean by involutive norm?
The norm of F star is the norm.
Ah, only this. Okay. Not C star condition.
No, sorry. The C star norm is smaller than this I norm, so
It's an isometry. Okay.
So now we have a norm on CC of G. We can talk about representations of. So a representation in a Banach algebra B is just homomorphism, which is constructed for this max norm that I just defined before. Or if you want, we can do this starting with. We're also interested in like representing this thing as acting on a space E. So that's why I wrote this definition as well. Particularly when E is LP of some metric, for example. So if this is a fractured R for representations, is a family of representations in this sense in some Banach algebra somewhere, then we can norm CC or G by these representations in the standard way. Supremum of the norms of psi of F, where psi comes from the class. So in particular, if you choose R to be all representations on Hilbert space, this will give you the max C star norm. Or if you choose R to be all representations on LP spaces, this will give you the universal LP norm considered by Rydell and Lupini, I think. Or you could choose R just to be the single representation, the regular representation, then you get the reduced algebra. So just a comment here. This isn't immediate because the way this is defined, the representations have to be contracted in a different norm on CC or G. So our representations have to be contracted. If these representations have to be contracted in our max norm. The usual definition is representations in Hilbert spaces which are contracted in the I norm, which I defined before. So I didn't have time to include it today, but through some estimates that show if you're representing on Hilbert space, for example, then if it's contracted in R norm, then it has to be contracted in the I norm as well. So that's where this comes from. What should we do now?
So I have a question. Could you come back? In general, you cannot be sure that this supremum is finite.
And we know why.
What do you know about your family? What guarantees that this supremum is finite? If not, it's not a norm.
Isn't F compactly supported again?
Yeah,
Yeah, but the family could be
It's
quite big.
yeah, sure.
So there are,
but, sorry.
so it's a semi-norm in general.
Yeah, okay.
Or taking value equal to infinity.
I guess we just avoid this problem.
So it's not a norm yet.
Okay, yeah. Once we.
So even if you restrict yourself to Hilbert spaces, it's not clear to me that if you allow all these representations, what guarantees that even if you restrict yourself to Hilbert spaces, you obtain a finite supremum?
So
In
Thomas,
general, even for system algebras, you cannot
Yeah,
be sure.
of course.
Yeah.
but isn't true that every such a representation is a contractive? It's just star homomorphism, so
Well, we're representing in Banach algebras, so they have no star. But our definition of representation is contractive in the I or in the max norm. So maybe that answers your question.
no, but for Hilbert spaces, this is a general fact that any such representation is a
Yeah,
what
Hilbert
a star
spaces.
homomorphism between C-star algebras, and such homomorphism should be bounded contractive, in fact.
Yeah,
Yeah.
but to be sure that you are mapping into a sister algebra, you must know that the domain is a sister algebra. But this is not a sister algebra yet. Exactly. Like the dense subalgebra, you want to complete it.
Aha, okay. You're right.
Know what could happen.
There are some technicalities to be taken care of. So now I want to persuade you that this is a good definition of algebra associated to the groupoid.
Sorry, I must ask another question.
Yes.
You are speaking about star Banach algebras, for which the star is an isometry.
So CC of G is a star algebra, but in general, we're representing in like operators on LP space, for example, or general Banach algebra.
And you are forgetting this star.
We might forget about the star. Yeah.
So how do you know that after this completion, even if this completion exists, how do you know that after this completion you obtain? You do not assume that after completion it is still an isometry. This star is an isometry.
Yeah, we might lose the star.
You may lose the star. Okay, I see. Okay.
So I want to persuade you that this is a useful notion, a useful thing to attach to the groupoid. So I show you the way I'll try to do this is to show you that we can find some information about the groupoid inside this algebra in some different ways. So one thing is I showed you that inside the groupoid is this inverse semigroup action. This we should be able to find that in the groupoid algebra. LP operator algebras are nice because there's more data in there. Like you can get your hands on something in the LP case. There's a measure space underlying it. So we would like that our groupoid data interacts nicely with the measure space data. So I'll try to show you that. And finally, if I have time, I'll look at simplicity criteria for this algebra. So for C-star algebras, there are some sensible good notions of what properties G should have to make the C-star algebra of the groupoid simple. And we want to see how that plays out in hierarchies. So pick up the first task. Semigroup actions and representations. So just to remind you that my groupoid can be written as the action of inverse semigroup S, which is the bisections of G, acting by partial homeomorphisms. So here S acts on partial homeomorphisms on X. And if we dualize this, we get partial automorphisms on C0 of X. This is one of these other kind of inverse semigroups act by partial isomorphisms that I mentioned. So I'll denote this dual thing by H hat. And here's the formula. And remember that XT is an open set. So this is an ideal of functions. We think of it as functions that are zero outside of the open set. So cross products by these inverse semigroup actions on C-star algebras have already been considered by Zeven back in the 90s, and a bit more recently by Hughes and Cell. So the procedure is more or less what you would expect if you know the construction of a cross-product C-star algebra formed from a group action. You define an L1 space. In the case of a partial action, L1 of my action is different. We take those functions for which f of t belongs to the functions living on the domain of ht. And the formula for the convolution product is not quite what you would expect. So here we have hs here and hs star here on this part. And that is because if you write the normal formula for convolution on L1 of a normal group action, say on C0 of X, it doesn't work because the domains don't line up with what you would want them to do. And this formula gets us around that. If you it's possible to prove that this formula gets us around that problem with the domains. But we have this one algebra. We can define covariant representations on Hilbert space in the usual way, and then complete to get a C-star algebra. And that's more or less what these guys do. So now I'll define a covariant representation in a Banach algebra. So what we're aiming for is these representations should have some connection to our Groupoid Banach algebra. So a covariant representation of this action on C0 of X by partial homomorphisms in a Banach algebra B consists of two things: a representation pi of C0 of X and a map V, which takes values in the unit ball of the second dual of B. I'll try to explain why this is here in a moment. This pair should satisfy some properties. Here we have a covariance condition. V should be a homomorphism of inverse semigroups This isn't quite the condition for like VSVT, it should be VST. But we can only do this whenever we multiply by something living on the right domain. Next, if E is an idempotent, then it should act as the identity on this ID. So I should tell you what an idempotent is. There. It's said that S, which are just E squared equals E. For example, T star T multiplied by itself. Well, the inverse semigroup condition is that this is equal to T star. So this is T star T again. Actually, all idempotents at this point inverse semigroup. So my inverse semigroup is a group. There's only one idempotent. So as we get further away from being a group, we have more idempotents. And if we think of VT as we want it to be a partial isometry, then V of an idempotent, VE, it should be like a projection. Somehow that's reflected here.
But there are two projections. Because it's a beginning source projection.
I didn't mention that, but yeah. I'm not worried about that. And the fourth thing is this, what we call a normalization condition. So it says that if we have an approximate unit in the right space, then VT should be the limit of this thing. So what we want to say is that if xt is compact, so this thing is unital, then we want I of 1 xt VT should be VT. That we want something like this, but in general, this xt here, it's not unital, so we have to work with approximate units. And that's where this double dual comes in. This limit is taken in the topology coming from the pre-dual of the double dual, coming from the dual of the. So just to reiterate, these are like representations which know about the inverse semigroup data. And what I want to show you is that our representations of the groupoid Banach algebra I defined before, they will have to have this form. So our representations of the groupoid Banach algebra, they automatically know about this action that lies under the groupoid or function groupoid.
So essentially, the image of a V fits in what? Do you need the whole unit ball in the double dualization?
I'm about to say some things about that.
Okay.
Okay, so yeah, this is what I said before. In general, asking for being in the unit ball is too restrictive. As I mentioned, we need to take limits, and it turns out that we have to use this pre-dual space to take these limits. this normalization condition, it's equivalent to, as it turns out, requiring that each of these things is a partial isometry. So we're working in a Banach algebra B. BT lives in a Banach algebra B, or maybe double prime. So a Banach algebra with either arms product.
So we need this double dualization only for this normalization and for being partial isometries.
Yeah, this caused us problems. We're often interested in like when B is bonded operators on LP space, and then we don't need to go to this double dual, for example. But the only way we'd sort it out in general is to so this there's a notion of partial isometry in a general Banach algebra due to Imberta, generalizing the idea of partial isometry B of H, partial isometry on a Hilbert space. And this condition turns out to be equivalent to our HVT is a partial isometry in Imberta's sense. So that's why we want this condition, because our inverse semigroup elements, they should be represented as partial isometries. So if VT is a partial isometry, then it has a generalized inverse VT star, and we want it to be VT star. That would be the natural thing to happen. This is almost the case.
At least to mark the effect.
I mean, not really. I'll say again, if we pretend that xt is compact, then we have like I of x t b t star is equal to I of 1 star or something like that. So at least when we're on the right space, we can expect this. Yeah, there are some other natural ways or some things that we can do instead of passing to the second dual. Yeah. For example, there's this notion of a dual Banach algebra due to Rinde, I think, which is a Banach algebra with a redual Banach space such that the pairing between them is nice in some way. So we could ask for V to take values in B, where B, the unit ball of B, where B is a dual Banach algebra, and use the pre-dual of a dual Banach algebra for these units, and so on.
So in L2's case, you could speak about von Neumann algebras.
Yeah, for example. In particular, representations on a Banach space E, like representations acting on B or V, it works nicely whenever our Banach space E is a reflexive Banach space. Then we have some less duality around, and it's easier to work with these things. So, sorry, one more time. This is representations which respect the inverse semigroup action which underlies the groupoid, and we hope to make some connection with our Banach algebra. So representations integrate to representations of L1 in the usual fashion. So then we define like a Banach algebra cross product, this thing, to be again the closure of this L1 algebra in the norm coming from this family of representations, covariant representations, which I chose here. In particular, I could choose all covariant representations in Banach algebras. That's a universal thing. So here's the theorem that I've been hinting at. There's a bijective correspondence between representations of our Groupoid Banach algebra in a Banach algebra B and normalized covariant representations of the inverse semigroup action in the Banach algebra B. So I want to interpret this as saying that this Banach algebra, it knows about the inverse semigroup action that underlies the groupoid, because the representations are the same thing as covariant representations. So correspondence it's like this. So this delta t is like a placeholder, like a characteristic function of the point t or something. It tells us that we're in the fiber of t.
Could you replace this bijective correspondence
I'm thinking about
by some universal property?
exactly, because when you have infinite sets, saying there is a bijective correspondence is not saying much.
Yeah, okay.
You must preserve some properties, otherwise it's going to be just some stupid bijection between two continuum.
Okay, well, maybe like this formula gives a bijective correspondence. But
Yeah, this is much better.
Is that better?
But I guess,
But easy
to quantify it or not quantify it qualitatively.
does it lead to a universal property of this construction?
I need to think about that. I don't know.
Because some constructions are universal only with respect to isomorphisms. These are not very good. But some are that every map
Yes.
through something factorizes uniquely.
Yeah, maybe we should think about that. You're right. So in particular, this is isomorphic to this. And for example, if we take R to be a class of all representations acting on some Banach space E, then it doesn't matter if I choose this is covariant representations or as representations of this of CC of G in the sense from the beginning of the talk. We get the same thing.
Yeah, I was thinking along the lines that these sets of representations should have some additional structure, and then the bijective correspondence should preserve it. That was my thinking. Yours was universal property.
What kind of additional structure?
Well, I don't know. Algal structure, perhaps.
No, it's rather the size, boundedness of uniform boundedness, something like this. So there's a standing warning that this construction may or may not exist.
Yeah, okay.
Got that.
Twice.
Now I want to talk about LP algebras. So I guess if you just think about group algebras, this goes back to Hertz, at least in the 70s, who thought about representing groups on LP space. And then Phillips was interested in LP versions of Hertz algebras, which have a groupoid model. And then there's some general theory was taken up by Eusebio and some of his collaborators, and also these guys. And we want to make a link with what they did first of all, and also again go down to the underlying data in some. So our framework gives a natural suggestion for how to define the LP operator algebra of a groupoid. We take R to be the class of all representations LP space for some measure mu. This is a reasonable measure in some sense.
What's the meaning of this localizable?
It means that the underlying measure space is nice enough in some way. These appear a lot in like Fremden's measure theory book or something. So I might be able to tell you on the next slide.
And what is the fullness of this groupoid?
As opposed to reduced. So there's also like a reduced LP groupoid algebra. So I'm just using full.
Okay.
The more you think it's reduced. So here's where I can remark on the complex versus real situation.
So I don't understand. So you are speaking about this dichotomy, reduced versus full. But still, in the case of full groupoid, you are assuming some restriction that these are representations are mu localizable.
Yes. So in our paper, we argue that this is a localizable measures is a reasonable restriction to make.
Otherwise, fullness, this full construction doesn't make sense. Okay.
So yeah, I can comment on the complex versus real case. Here are the standard definition of representation that I gave before only works in the complex case. In the real, basically what happens is if you think of this according to the previous section as C0 of X cross product by inverse semigroup S, our representations when we restrict them to C0 of X, they should act on LP by multiplication operators, by diagonal things. And this is automatic in the complex case, but it's not automatic in the real case. We have to add that as an assumption in the real case. It doesn't happen on, but we want it to happen, so we write it in.
What you have to add in the case?
That a representation of this a representation in B of LP of mu, it has to take C0 and X to multiplication operators. That's what we have to add.
So why for C you don't have to add this?
Because it's automatic in complex case. Representations in complex case automatically preserve positivity. And then that means they have by multiplication operators. In the real case, this doesn't happen. So just to say it again, this definition reduces to the one considered by Białymstoku. I explained before that our definition of a representation on LP space is formally different from theirs, but we can prove they reduce to the same thing. So we want to kind of understand how these representations act. So we know that representations of groupoid Banach algebra they're covariant representations, so they're pairs. The pairs pi from a V, and I said before that the representation of V of the semigroup S, it should act as partial isometries in some sense. Like the inverse semigroup looks like partial isometries, and we hope to see that when we represent. But in the LP case, there's a couple of different things you can do. So let's give this definition of partial isometry. Or what you could do is you could just copy the definition of a partial isometry of Hilbert space and adapt it to the LP case. What we call LP partial isometry.
So how do you make this L2 construction?
It's on the next slide.
Okay.
But first I'll tell you about these. So underlying this thing is a Boolean algebra. This is a space, measurable sets, and measure. And then we get a Boolean algebra by identifying null sets. By the way, this the condition about measures that you asked about before is a condition, at least partly, about this thing. It should be Dedekind complete or something.
I checked. It literally means that if you have any set that has positive measure, then it should essentially contain a set of finite positive measure. That is one thing. And the other one is that for any family of sets, there should exist an essential union of them as a measurable set. So a union up to a null set.
Okay, yeah, which is like up to null sets is what I'm doing here.
Yeah.
So then we have this definition of a set isomorphism. It's a map from measurable sets to measurable sets, which at the level of this thing is a Boolean algebra isomorphism. This was all considered by Phillips. But of course, we have an inverse semigroup. We don't want it to act as isomorphisms. We want it to act as partial maps. And so a subspace for the sub-objects of this thing. Well, we take D and we intersect the measurable sets, and we restrict our measure. And then a partial set automorphism is a map between two things of this form, which is an isomorphism at the level of Boolean algebras. That's what Phillips defined to be a partial set automorphism, or what Phillips used as a partial set automorphism. And then we get an invertible map at the LP level. Just takes characteristic function of C to the characteristic function of phi of C. This notation here is not good. It's only a partial map on LP. So it goes from some subspace of LP to some other subspace of LP. But this one, it won't be an isometry. So to make it an isometry, you have to add this derivative here. So this thing, U sub phi, is called a partial automorphism of LP. And, if you look in Phillips's papers on LP Kuntz algebras and the like, he requires that our representations are as partial automorphisms in this sense. He calls them spatial partial isometries.
So for P equal to 2, this reduces to? The usual partial isometry.
P equals 2 is complicated.
It's an extension of
Yeah,
and also
yeah,
partial
it is an
isometry.
extension. But in the background, there's this Banach-Lamperti theorem, which is not valid for 2.
Okay.
So that's our first option. Then the second option, the LP version. So P is any Banach space. Then there's this notion of an LP projection that's been around for a while. It's an idempotent subset that interacts with the norm in this way when P is finite, or this way. This is just the Pythagorean condition in P equals 2. And so if E is a Hilbert space, then I'm a problem projection is an LP projection. And except for trivial cases, every Banach space E, there's only, as far as I remember, one P, at most one P, for which there are non-trivial LP projections. So our definition adapting the partial isometries on Hilbert space is this one. It's a contracted map. Contracted map T, which has a contracted generalized inverse. In this sense, these equations are satisfied, such that these two things, like that should be the source and range projections, are LP projections in this sense. Yeah.
And star meaning what?
Well, T star is just the name I give to the generalized.
Is unique?
At the minute, no. I'm not defining it to be unique, but it will turn out to be unique, at least in some cases. So we could also, I just scrolled it.
So sorry. So this could be LP partial isometry with respect to many choices of T star. If it's not unique.
In theory, yes. If it's not
is enough to have one T star. Or should it satisfy this condition for all such T stars? The T star T and T star are LP projections for all such T stars, okay, satisfying these conditions. If it's not unique.
Yeah, I'm not sure. I need to check. I don't remember off the top of my head. So we could also try to represent our inverse semigroup in LP space as LP projection or LP partial isometries in this sense. But it turns out this is the same as spatial partial isometries.
It is strange that P equal to 2 is excluded in this theorem.
Yeah, I'll mention that on the next slide. So I think of this as like the underlying data of a representation on LP space. We want it to act by partial isometries in this way that especially spatial partial isometries, like we really know how it acts on the measure space. So that would be good for us to understand. And in fact, Phillips actually required that in his definition, that they had to act by spatial partial isometries. So the theorem is every representation on LP is a covariant representation, as you know from the previous section. And I represent C0 as multiplication operators, and V represents S as spatial partial isometries, or equivalently as LP. So in fact,
in the complex case.
Yes, in the complex case. This is the problem. Yeah. So we actually, this is forced by the Groupoid model. The representations have to act in this nice way. Basically the message here. Equivalently, looks like this. It's multiplication by something here. And we have this family of partial set automorphisms such that VT is the spatial partial isometry corresponding to the set automorphism. I defined before. So just a remark about how we prove this. Is this Banach Noncommutative theorem? If P is not equal to 2, then every partial isometry is spatial. So this is why I have to exclude 2. This is the comment I made before. Phillips required his representations to be by spatial partial isometry. But we proved we don't have to require this, it happens automatically. So in the last few minutes, let me quickly tell you about simplicity. When is our Banach algebra? Simple Banach algebra, no non-trivial ideals. So there are some prototypes for these results in the C star place. Here's an example by Brown, Clark, Farthing, Simmers. For a Hausdorff second countable groupoid following our equivalent. G is topologically principal and minimal if we only have the C star, the reduced C star algebra, which is simple. So there's a few different like freeness conditions out there in the literature, like essential, topologically principal, topologically free. So we're going to use topological freeness. Sometimes they coincide, like in Hausdorff groupoids, some of these things coincide with each other. But in general, topological freeness is weaker.
But is it the same as in the case when you simply speak principal and free, that the difference between the two concepts is properness of an action?
This was investigated in this paper.
Okay, so if you are free and proper, you are basically principal.
It's a groupoid, it's a groupoid case.
No, it's a naive question.
So the definition, topologically free means there's no non-empty open set that doesn't meet the unit space on which the range and the maps agree. And minimal if there's no non-trivial set, open set inside the unit space for which the domain belongs to you, implies the range of gamma belongs to you.
So topologically free means that there are no non-empty open. Beyond stabilized by these parts. Instead of fixed points, you exclude open.
Yeah, so that's very much in the spirit of topological freeness with group.
This is okay.
So the idea behind these proofs is the same. Like, if my groupoid is topologically free, then an ideal of this thing, for example, it has to intersect with, it has to contain an element that lives on the unit space. And then minimal says if there's a non-zero element like supported on the unit space, then the ideal generates is the whole thing. So these two things play off against each other and give you simplicity. In the C-star case, it's not too difficult to go backwards from 2 to 1 because you can write down this orbit representation, it's called, and I'll allow you to go back. So first,
so you mean that in the case of the action groupoid, it reduces to minimality and topological freeness of the action.
Action, yeah. These are groupoid generalizations that we just so first we have to take care of this reduced. I don't know what happened there.
Could you replace these conditions by conditions phrased in terms of bisections?
Yeah.
Okay. But only for the étale groupoid.
Probably, yes. I'm not sure. I'm not sure beyond the tile what happens at all. So of course we need to have reduced here because otherwise we have the kernel of the regular representation. So we want to avoid running into this problem in the Banach algebra case. So to do this, C0 of G in the Hausdorff case means C0 of G. In the non-Hausdorff case, it stands for bounded Borel functions. Just for this talk, think of it as usual C0 of G. So then, this is based on Reynolds' work. What we did was we defined what it means for a groupoid Banach algebra to be reasonable. I'm not going to give that definition just as I don't have time. But for reasonable groupoid Banach algebras, this inclusion of CC into C0 it extends to this map that was first considered by Renaud, which goes from the groupoid algebra to C0 functions. This is a bounded linear map. Of course, convolution properly here, it's not modified. C0 is not a Banach algebra for convolution, but this thing is still a CC convolution bimodule map. And the kernel turns out to be a closed ideal. And so we need to get rid of this closed ideal, which is always inside our Banach algebra. Therefore, we say that our reasonable Banach algebra is reduced if this map is injective, this Renaud map is injective. And we can always reduce a Banach algebra by taking the quotient by the kernel of this map. And it's possible to prove that once we do this, we get reduced. This reduces to the notion of a reduced groupoid C-star algebra or a reduced LP groupoid algebra. If you define these in the regular representation on L2 or T or C, the kernel turns out to be the kernel of this map. And finally, the simplicity theorem. We have these two conditions again. G is topologically free and minimal. Every reduced algebra is simple. To go back to one, we need something where we can get our hands on the like a representation of something. So I've written here F1 or F infinity is simple. So here we have if you just want one algebra, you can do it. Reasonable algebra is simple, and C0 of X fits in here as a maximal subalgebra. So I'll finish that. This reduces to some simplicity criteria for Groupoid algebras, like LP algebras that are out there already. So I plan to talk about the non-positive case of simplicity, but I'll say thank you.
Thank you so much. Okay, we have many questions from the room. How about any questions from the Zoom? Anybody? Like collaborators? No, collaborators are gone. Ludwig, Mark, Adam, any volunteers? Okay, Zoom is silent. So any more questions from here? Nope. Comment.
Yes, I have a question. What if you have ideals? Can you relate these ideals to something in the structure of the point?
What kind of thing are you looking for? Like,
in a non-free case, if you have.
Yeah, I mean, this is a simplified version of the simplicity theorem. There is also like a more general version where there's this thing called the hidden ideal, which is like the largest one that meets the C0 of X. So we could talk about ideals, like we could have that ideal and like we can kill that ideal.
So could you say it?
So I'm not sure what sort of thing you're looking for, but there is this notion of like a largest ideal inside the algebra that doesn't meet C0.
Okay. Okay.
So there could be ideals living in there.
And this corresponds to what on the side of the groupoid?
I'm not sure actually. I don't know.
Can you see, for instance, fixed points of the
inverse semigroup action,
for instance?
I didn't think about it, but
not ideals, maybe some representations.
Works a bit like the group case in this point of view, like the action of a group on a set. If you have fixed points. I don't know.
Could you come back to the last slide?
That's the last slide.
No. With the text, mathematical text. Okay. So the last theorem. Any reduced reasonable this convolutional algebra is simple. So what are these conditions for being reasonable?
These are the conditions that we need to define this. Okay.
This yes.
So somehow these are the ones for which it's reasonable to ask the simplicity question.
So it's like this relative expectation.
Yeah, we need these conditional expectations.
But condition for expectation, yes. Raynaud.
Yes, yeah, this is based on Renault's stuff.
Can you check this property? Knowing something about your groupoids.
Which property?
That first of all, that this algebra for all possible representations exists.
Yeah. Okay.
And second, that it satisfies this the existence of this Raynaud conditional expectation.
Yeah, it doesn't seem that reasonable. I think maybe
Can you interpret this expression reasonable in terms of the groupoid?
oh, it's in terms of the norm. Like we have to have this the norm of the infinity norm of f needs to be smaller than something some other norm.
Okay.
I don't know if there's a way to put that into groupoid language only.
So at least in terms of functions. Oh, I have another question. How functorial is this construction with respect to the groupoid?
That's a good question. That's one I'd like to know.
What about Zakrzewski morphisms?
I don't quite.
In the classical case, sister algebra of the groupoid, convolution sister algebra, is a functor with respect to Zakrzewski morphisms between groupoids. So you have something like this.
We didn't think about that at all. Maybe we would like to. It would be nice to have some functoriality statement. Sure. I don't know how realistic it is.
Okay, I'm good.
Okay, I suppose, yeah, you have a question, go ahead.
Can we define the continuous case of this?
I mean,
Yes.
that would be going outside of the Ital setting, and I don't think like this inverse semigroup picture. I don't think we have it, and I'm not sure. Not sure how one would do that.
Thanks.
So probably you would need to replace these projections related to these local bisections by the action of the Lie algebra, Lie algebroid, okay, on some smooth subalgebra. But there are problems with making it the topological continuous, because it's like derivations, they act unboundedly.
Okay, everybody happy?
But you're right. There should be a parallel theory for Lie groupoids. Maybe not in the sense of this completion, but maybe some pressure theory.
Okay, but that is yet another story. So let us thank Andrew again. Thank you so much. And we adjourn.